Can I start? Okay. So, welcome back everyone. Today in this session we are going to talk about the storage of hydrogen. Now, when we are coming to the hydrogen energy sector, we require a few sequential steps. First is obviously that we need to generate the hydrogen. In yesterday's class, I talked about the electrolyzer system. Electrolyzer, what does it do? It generates the hydrogen. Now, if we want to have a more greener solution, we can have a renewable energy like solar system to generate this hydrogen, this electrolyzer. Now, after that, we need to use this hydrogen. So, is it always possible to use the hydrogen where you produce? No, it is not always possible. So, in that case, what you can do is that you might be requiring to transport this process from one place to another place, or you might be requiring that maybe you are producing the hydrogen at a certain time of the day, maybe you need to generate the electricity at a later time of the day. So, you need to store this hydrogen. So, that is why this storage comes in picture. So, so that the hydrogen that you store, you can use it later for the application purpose. Now, for application or to generate the electricity from the hydrogen, hydrogen is nothing but a fuel here. So, to generate the electricity, we need a fuel cell. Now, this hydrogen, the storage of hydrogen is particularly very challenging, and in that case, we are going to see why it is challenging. We all know that hydrogen comes at the very beginning of our periodic table. So, now that is why the density of hydrogen gas is only 1/10 of natural gas. It is very low. Even the liquid hydrogen, that is also very low density. But the problem is that with the low density also we have the advantage of this hydrogen is that we can have a much larger amount of energy per unit mass, that is 120 megajoule per kg for hydrogen, which is 3 times of the gasoline. So, per kg of gasoline we can get huge amount of energy, we can get 3 times of that of gasoline. But how is the volume of this per kg of hydrogen? That is also very huge. So, we need a huge container to, if we want to store it in a gaseous form or in the molecular liquid form. So, that is why it is very important to store it properly. Why it is also very important to keep the safety aspects in mind? Because we know that hydrogen is extremely flammable, and if we catch fire, the ignition, the flame velocity is 346 centimeter per second. So, if there is a hydrogen fire here, in a second it will go 346 centimeter. So, it is very fast, it is 8 times of that of methane. So, the fire will progress very rapidly if there is an accident. Okay. So, that is why we need to keep that safety in mind while we are storing the hydrogen. Now, we are going to see what are the methods that we store hydrogen. Now, for storing hydrogen, I already told that we need the hydrogen storage for intermittent use or for transport from one place to another place, that is the purpose of storage. Now, the types of storage are mainly of 3 different types. One is the physical storage. In physical storage, what do? We just keep the hydrogen in its own form. So, we make the temperature very low or the pressure very high, so that it can keep it in the physical form, in its own form. In chemical storage, we make a complex or a conjugate with another compound and we store it. In a membrane based storage, what we need is that it is very often to find from natural sources or from other sources hydrogen gas mixed with some other gas. So, what we do in membrane based storage mainly is that we store that mixture of hydrogen gas with other gas, and whenever we require this hydrogen energy, we use the membrane to selectively transport the hydrogen energy from one side to another side. So, here the purpose of the membrane is that we do not have to convert the hydrogen in another form, whether in a liquid form or in a conjugated form, but what we do is that we transport these from one place to another place by help of selective transport mechanism. Now, here what, as I was telling that let us see a little more details about these three types of storage. Generally it is stored in physical storage in the molecular form. Typically the pressure requirement is very high, 350 to 700 bar. So, you can understand, because this hydrogen is so light in nature, so that is why we require very high pressure and very low temperature also, minus 250 degree centigrade, to store it as a liquid. So, you can imagine the amount of mechanical energy you require just to store this hydrogen in a physical form. Now, the chemical storage is what? It can give you a metal hydride format. I will just try to take the help of this metal hydride. So, metal hydride, what they do? They go through a cyclic process of absorption and desorption. So, in the absorption slide, what we are doing in the absorption cycle, this metal, they just conjugate with the hydrogen molecules, and at the hydrogen molecules attach themselves surrounding the small particles of the metals. That is the metal hydride. And now when we change the temperature of the system, just by altering the temperature of the system, we can switch between absorption and desorption cycle. Then we can go from this hydrated to the non-hydrated sample. So, we can get the hydrogen out of the system. So, we need to switch the energy, the temperature of the system. So, that is a part of the chemical storage system. We can use metal hydride, which is more common in a chemical storage, or we can use liquid oxygen carrier, liquid hydrogen oxygen carrier. What are those? Basically, they are stored in form of ammonia or methane, this kind of format, a different chemical form. And if you need to change the ambient condition, then you can release. So, basically here you need to produce a chemical reaction in order to release this hydrogen. So, in this system you need to produce a alternate chemical reaction. That is why we have this kind of complexity in the chemical reaction storage. Now, that was about the chemical reaction storage. In the physical reaction storage, you can compress it to a very high temperature, very high pressure, and to a very low temperature process, or you can have it compressed with the cryogenic storage option. Okay. So, we have given here a few options of this storage system, the physical based storage. We can have compressed gas in a very high container, very highly sealed container. Also, we can have it in a cryogenic container like this. Or otherwise, if we are having a material based, then we can have it in form of MOF or adsorbent or liquid organic or industrial hydride, etc. So, these are the options which are more common, or chemical and physical storage. Now, as I was telling that getting gas stream with hydrogen gas mixed with other gases, that is very commonly found in industries and natural sources, and for that we can very cleverly we can use membranes in order to utilize these hydrogens. So, how do we do is that, let us say that I have a mixture of carbon monoxide and hydrogen, I have a palladium membrane. When this mixture comes in contact, these hydrogen molecules, they get dissociated with H and H plus, and then they get transported through the membrane. Okay. So, this is practically allowing only the hydrogen, not any other molecule through it. So, on the other side, or the permeate side, or the downstream side of the membrane, what we are getting is a hydrogen gas. So, this is what is one of the typical application of a inorganic membrane, inorganic metallic membrane. We can have some specific polymeric membranes, but very dense structure. As in the previous section, in the previous lecture we were listening to various kinds of phase inversion and membrane preparation technologies. Sir was mentioning about the when we are making gas separation membrane or membranes for this type of application, we do not expose it to the water or non-solvent. What we do is that we do evaporation of the solvent for this polymeric membrane, so that we can have a very dense structure of the membrane. What are the typical conditions where when we are having this kind of polymeric membrane? So we can have it exposed to a vacuum. Vacuum will do the evaporation of solvent very fast, and also we can do the do this evaporation of solvent in a inert atmosphere. Okay. So just keep in mind that if we want to have a very dense structure, if we want to have a polymeric membrane for this kind of application, we want it not to be prepared by a non-solvent technique, but to be prepared by a solvent evaporation technique. Okay. So this metallic membrane and polymeric membrane, this can be a very cost effective solution, but at the same time it offers a lower selectivity. Ceramic membrane, we know that it is a very high temperature operation. So we can go for very high temperature operation with these techniques, and the advantage is that you can get almost 100% pure hydrogen if you engineer the membrane accordingly. So you can have very low energy consumption, because again you are not creating very high pressure, you are not creating very low temperature. So these conditions when we are getting rid of, then energy efficiency goes up manifold. Okay. So it is also very compact and stable, because we have less amount of mechanical components through it. Okay. So if we compare these membrane based storage with other conventional storage, one thing we can see is that I was telling you about the polymeric storage. So whatever preparation method you use, still it is less selectivity is less compared to the inorganic membrane if we have a polymeric membrane. So you can have some other options like MOF or other adsorbent if you just impregnate as a form of a composite material, as a form of a additive for your polymeric membrane. In order to that, you can increase the enhance the separation efficiency. So it is preferential transport of hydrogen which is being used in a membrane based technology. So much lower energy consumption. In the hydrogen purity level, you can go manifold. So you can get the means almost 100% purity with this kind of membrane storage system. You can use lighter materials also like graphene or MOF as a membrane material, but when we are having a cryogenic hydrogen storage system or a liquid hydrogen storage system, there are a lot of auxiliary components adjusted. Okay. So that's why it can be lighter. Operating pressure, as I already told, it is lower. Now thermal stability is also comparatively higher, but compared to this we need to be more careful, because there are certain components like MOF which will degenerate if you go up to very high temperature. Okay. So that's why we do not need very high temperature, but we need to be very careful with the temperature level. But safety is that there is one problem with this conventional storage, or one challenge with the conventional storage is that because we are using a very high pressure operation, so that's why in case there is a leakage in tank or anything, then the accident goes very huge, spreads very fast. But if we have a lower pressure requirement like in membrane, obviously you can have a lower risk. Okay. So but one thing is that today we need to focus more in today's scenario to make these options more flexible or more economic. Okay. Now we know that membrane is practically selective transport. So it is blocking other gases, it is only allowing the hydrogen but not allowing the CO, okay, or CO2. These kind of materials are not being allowed to pass. That is the mechanism. Now what is the mechanism of transport? Through which this mass transfer happens? in yesterday's class sessions we were talking about the diffusion, solid diffusion, and also we can see that we have talked about in the RO what kind of mass transfer happens. So, here we can see both types of diffusion, active and passive transport, both kind of diffusion. What is active transport? Active transport is like hydrogen itself is getting diffused through the molecule. What is passive? Passive is that it is getting itself attached with another molecule, and that molecule is getting transported and separating hydrogen on the other side or the downstream side. So, that is all kinds of transport selection activity appears. But now again, what type of polymer or what type of membrane material you are using, that is important for optimizing the material or optimizing the operating condition of your system. Okay. So, now let us see that what form the metallic membranes offer. Okay. So, in the previous slide I was talking a little bit about the polymeric membrane. In the metallic membrane what does it look like? Mostly the metallic membrane used in the industrial or real life scenario, they are of ceramic in structure. So, what we see is that we have hydrogen and helium gas going through one side, and then they can diffuse through these metals and go in an atomic form and go to H2 form on the other side. So, these red, the molecular form is divided in the atomistic form, and on the other side it is going again to the molecular form to get the hydrogen energies, hydrogen in a molecules. So, now we can have palladium or palladium alloy in order to reduce the cost of the system, or some non-palladium metals like nickel, vanadium, etc. They can also be used for this type of operation. Now, let us see a little bit. So, this thing I already told you that when the membranes are selectively transporting hydrogen molecules, they are going through adsorption and dissociation first. So, these molecules, this is a mixture of CO2, CO and hydrogen. When they are getting in contact, then adsorption happens and dissociation happens, means H that happens. Then ionization diffusion, that diffusion can be active or passive. Desorption and recombination is that these are getting in a molecular form. So, this is the transport mechanism. You can have very high purity level. Now, let us see how they are rolled, how they are making the, how they are made, these kind of membranes. So, now in this structure you can see that you can have a porous support, a stainless steel ceramic support onto the membrane. Onto it you can have a palladium loading. So, what you do is that you can have two rollers rolling in opposite direction and pass a sheet of steel or support system through them, and onto these rollers you can have this palladium getting, and you can have it etched onto the surface of this support system, so that you can have a coating like this. So, now one thing, as I was telling you that palladium membranes are very popular nowadays in type of hydrogen energy. So, all types, all stages, preparation, storage and application, all these stages hydrogen is very popular. But one thing we have to be careful about the reaction with sulfur. So, we have to control the reaction with sulfur so that it does not pollute our membrane, or we do not lose the efficiency of the membrane. Okay, not only sulfur, it is also corroded by carbon monoxide very effectively. Okay. So, challenges and solution, as I was telling that you can get very ultra high pure, but at the same time they are used and in terms of fuel cells and energy, etc. One more thing that you can have with the membrane is that ceramic membrane. So, we have till now seen about polymeric and metallic membrane. Now, what are the ceramic membrane? Ceramic membrane is basically used whenever we need a very high temperature operation. So, like zirconia, alumina, silica base, they have a excessive very good thermal resistance. They allow selective permeation of energy. So, here in this system we are seeing that there is a catalytic conversion. So, what we have here is that we have a membrane, over it we have some catalyst converted, and here we are basically storing hydrogen in terms of other chemical compound here, and when we are in the lumen side, inside the membrane core, we are allowing the hydrogen, and here see this organic molecule we are allowing. On the catalyst side, we are getting the hydrogen separated, hydrogen and carbon dioxide separated. So, this is basically one of the example when we are using ceramic form of the membrane in order to this temperature, this reaction requires very high temperature operation. So, this is practically one of the storage system where the hydrogen was stored in another form like in organic material. Now, they are in this particular paper they have reported that you can use this type of membrane for easy transportation or easy storage. So, you do not have to use hydrogen in its molecular form. So, you reduce the risk associated, but at the same time you can use the membrane. But at the same time this membrane efficiency is very high only when you use very high temperature, and so that you need a ceramic type of membrane for this operation. Remember, there is a catalyst coating onto the surface, and that is enhancing the transport, or that is enhancing the separation or generation of hydrogen through this scheme. Okay. Now, you can have, in order to enhance the properties like permeability etc., you can impart some of the other additives into the system to make it a composite materials like microporous ceramic membrane or dense ceramic membrane, so that you can have we can have more selectivity or more stability of these membranes. Okay. Now, in this course we have been very often talking about composites. So, composite, what is the role of composite? Why do we use composite? We already have so many options already, the metallic, non-metallic etc. But if we see each and every type of material, they have their own advantage and disadvantage. Basically, composites are taking the advantages together. So, that is the role of the composite. So, you can integrate polymeric, metallic and ceramic layers. You can either have it layer by layer assembly. So, one thing that is one possible scenario is that we can have this kind of membrane, like say this is a matrix of polymer. You can have small materials impregnated like this. So, this is dispersed phase of additives, or you can have layer by layer assembly, you can have 2 layer, you can have 3 layer. So, layer by layer assembly is that is how you can have a composite. So, that is why these layers are made up of different materials, and they are enhancing the mechanical stability, they are enhancing the thermal stability by using this composite approach. Now, these composites can be of polymeric, metallic or ceramic polymer or multi-layered composite membrane etc. So, they can be engineered very effectively to improve mechanical strength, utilize. So, one thing we have to be very sure about when we are using any kind of operation like this, that we are not the membrane materials are not leaching out from the membrane. Okay. Whenever we have any composite, not only for gas purification but also for liquid purification, during this operation, during the operation process, if the membrane material leaches out from the treatment, then the membrane efficiency goes down. So, we while characterizing the membrane, while making a new membrane, we always test the stability or whether it is leaching out. Those things are very important. Like I would like to say about one particular system here. So, we all know that there are these membranes like Nafion or PTFE membrane, they are very, very popular. Now, what many researchers all over the world they are now doing is like they are taking polymers like Nafion and they are making some additive like say metal phosphate or carbon nanostructure like carbon nanoanion or graphene. They are very popular additive as a choice. So, they are inserting those into this material. Now, yesterday I was talking with you about the water channels. Now, what these additives are doing is that they are not letting these water channels to collapse at higher temperature. So, you can enhance the thermal stability of the membrane by incorporating this kind of additive into your system. Now, let us see that when beginning this lecture, I told you about that when the hydrogen is stored in molecular form, we have physical and chemical and three distinct categories I told membrane based. But membrane cannot be used in these physical and chemical categories. It is not so. Membrane can be used in physical storage and chemical storage also. Okay. So, in physical storage, how can we use a membrane or where the membranes are used in physical type of storage is that what we are showing here is that one liquid hydrogen tank which is developed by or which is used by Airbus. Okay, Airbus, even we all know that it is a very famous aeronautical company. So, what they do is that they have a hydrogen container and they have to seal it very effectively. Okay. So, there are many heating and cryogenic arrangement all throughout the system. They are developing they are insulating the whole tank very effectively. But now, where is the membrane here? The membrane is basically at the outlet sector. Okay. Outlet sector. So, what they are doing is that they are allowing at the side in this Airbus membrane, they basically use palladium type of membrane or you can have other options like polymeric or ceramic or graphene based membrane which are used by other companies. What they use is that instead of, why palladium is there? Instead of having 100% pure nitrogen, you have a option to store, hydrogen mixed with contaminated with other gases or mixed with other gases like hydrogen nitrogen mixture or hydrogen carbon dioxide mixture, etc., which are more commonly found, and they do not require that much of high pressure or that much of low temperature, so that you can reduce the energy component, energy requirement of this surrounding material. Okay. Now, this outlet pressure, this outlet channel, if you have a palladium component or palladium membrane here, but you cannot use the hydrogen mixed with other gases. So, in order to get the pure hydrogen format, you have to separate out the hydrogen, but you have to selectively use the hydrogen sources rather than at the outlet sector. Okay. So, even this kind of system it is being tested in NASA also. So that they are so much promising and they are very, very useful for hydrogen transport and distribution system, so that pipelines and tankers can be easily maintained with this kind of technology. Now, in the composite materials, as I was telling, that we have options like zeolite, metal organic framework or covalent organic framework. They can be nanostructured or they can have a performance considered for the, now these are some options that we can have, is that this zeolite is one of the very popular option for storage of hydrogen. You can have MOF also, you can have graphene based materials also to be inserted into your polymeric or ceramic membranes. But what are the factors that you should be keeping in mind before choosing the material that is that you can use in your composites? You can have very high selectivity, you should aim for a selectivity like 100%. The membranes should be very much durable. Okay, so for that zirconia has been proven to be offering very high durability. So the permeability should be also high. So when you are making a composite, it should not happen like that the hydrogen gas which is coming out of your system, that is coming at such a slow rate that it is not useful for your application. So that is why permeability should be high, and for that graphene oxide has been chosen to be, or graphene oxide has been proven to be very useful in this technology. Okay. So now what are the options that we have for enhancing the technology, enhancing the system or enhancing the performance of the system is that you can have different MOFs being engineered all over the world, different structures of the MOF. You can have surface modification like plasma treatment, or you can have hybrid cost effective solution like polymeric and ceramic material for industrial application. Now, I was telling you something about this transport mechanism through the membrane. Now, what are the way the membrane diffuses through any porous membrane or any dense membrane? So, transport mechanism, as I was telling, that there are mainly you have a active transport where the hydrogen molecules or the water. So, this is basically they are showing here porous membranes. Porous membranes are for more application towards the liquid purification system. So, in these porous membranes you can have active transport like this, that the contaminant or the water molecules, they are transported as it is, or they can attach themselves with another molecule and being transport. They can have all together they can go inside. So, you can see a little bit of partial or full pore blocking. So, these are some of the transport mechanism of the fouling mechanism or the transport mechanism through the porous membrane. But in dense membrane things does not happen like that. Dense membrane, like which we should use for this kind of the like hydrogen application, where the transport is purely by diffusion. There is very little effect of convection through it. So, we do not have pressure gradient onto two very strong pressure gradient onto the two sides of the membrane, permeate side and the retentate side. What we have is that mainly diffusion by the help of the hopping mechanism or through this vehicular transport system. So, that is the dense mechanism. Hydrogen only diffuses through a membrane like this. So, hopping, as we know that hopping mechanism is like we have different functional groups onto the sides of the polymers, and the hydrogen, the polymers, and the hydrogen proton, they just come and sit and they just jump on that. So, this is called the hopping mechanism. This is purely a diffusion variation. Or we can have vehicular transport, is that the water molecule is getting transported, this water plus H plus, they are getting vehicular, so water molecules is carrying the protons with it. So, these are the diffusion mechanism through any kind of such dense membrane, whether be it a composite or whether be it a purely polymeric membrane. Okay. Fueling station. So, fueling station also membranes can be used. So, we can use composite membranes also for this type of membrane, or you can have metallic membrane, which is more common in this case. So, where they are coming in picture? So, in the metallic, in this case what we do is that in the fueling station is that we have the many hydrogen powered cars are coming in market. So, for that at the fueling station what we see is that during the fueling, here at the nozzle we have some particular membranes installed, so that they can have a selective transport during this case. Okay. So, what are the challenges that we should be benefited or we should be keeping in mind? Because durability, if it is not durable or if it is at least 1000 cycles, it should withstand. Otherwise, this frequent changing of this durability can be a problem in this case. Okay. It should be economical also, and hydrogen purification because we need a very high standard of hydrogen purity level. So, that is why these kind of membranes are used in this type of operation. We have to be very careful about the pressure, because if there is a leakage in hydrogen during this refueling, what will happen? A very big hazard. So, do you know about any regulation about usage of mobile phones in petrol pump? You know? So, why do they stop you from using the mobile phones? So, what is the reason? It's static charge. Yes. So, actually what it used to happen earlier is that because of static charge, some of the mobile phones, because of heating and many other issues, there were some incidents in petrol pump that they used to catch fire. Okay. Now, imagine what if that regulation has come into picture because of why this risk of catching fire with this heating of membrane or static is there, because there are some vapor of petrol, vapor of gasoline roaming around in actual petrol pump. But imagine if there is a leakage in hydrogen container and you have heating or you have a spark in your membrane, what will happen? Everything will go like yes, boom. So, that is why we should be very much careful about this purity level or this hydrogen production system. Okay. Now, there are some advantages, as we have told, that you can have very high purity of your system, you can have very compact and scalable operation, lower operating cost, but the challenge that remains is that we have to have more durable membrane. Zirconium is good option, as I was telling, but we need to have more durability in order to have a more widespread application. You have to be careful with the permeation rate also. Permeation rate has to be a optimized level, because too high of a permeation or too low of a permeation, both are causing a problem. We can have a high initial cost. High initial cost can be like, if we have palladium is very efficient. We have been talking about palladium so much. Palladium is very efficient, but at the same time very costly. So, that is also a concern for the scalability. Scalability, we know that membrane technology is a very highly scalable technology. No problem with the technological solution. Problem is with the material. Imagine when in an industrial scale we are using palladium to a high quality, it is getting the cost to be very high. So, we have to find an alternative to this kind of solution. So, that is why scalability concern is also there. We can have, so next I am coming to the question like how to select your membrane. So, we have talked about many types of operation, many types of compositions of our membranes, but the main two factors that come in picture are the selectivity and permeability. Palladium silver based membranes, they give you very high selectivity. Zeolite membranes comparatively less but still good. Polymeric membranes selectivity is comparatively low. So, these are some of the membranes that are most commonly used for these kind of operations, but permeability of these polymeric membranes are practically very high. So, they are basically counterintuitive. When you have a high permeability, selectivity goes down. When you have a high selectivity, permeability goes down. So, but both the things are important. So, you have to find a solution between the, we have to find a solution between the balance. Okay. So, that is why that is why when we need very highly permeable solution, then we have to choose on which type of permeability we need to use or which type of membrane material we need to use for this kind of membrane. Now, what are the temperature conditions that we use or pressure conditions that we use? We have been talking that we require less pressure, we require less extreme temperature. So, zeolite and MOF membrane you can use up to 250 degree centigrade, but for palladium membrane you can go up to from 300 to 600, or polymeric membranes are something which you can be more relaxed with the temperature, you can go up to 150 or 200 degree centigrade, no problem. But pressure is that inorganic membrane or inorganic alloy membrane, they can withstand very high pressure. So, that is why these alloy membranes, they can withstand up to 30 bar without considering or without affecting the selectivity of the membrane. MOF based membranes also has, or composite membranes, they also have lower pressure selectivity. So, if you want to reduce the selectivity, or if you want to reduce the pressure requirement of your membrane, you can have MOF polymeric composite membrane without compromising with the efficiency. If you have if you do not want to consider, or if you do not want to reduce your efficiency of the membrane, but still want very high thermal stability, in that case porous ceramic membrane can be one good option. So, now energy efficiency, what is energy efficiency? Basically energy efficiency is how much energy you need for producing of 1 kg of hydrogen. For membrane we have seen that it is considerably higher than other conventional technologies, but this efficiency can go down given to some specific conditions. Like if the factor is affecting the factors that can affect your energy efficiency, they can be high permeability, or if there is any sudden change in operating condition, or if you are changing the material properties like that. So, for that what are the typical properties of the membrane that we should use is that when we are having very high pressure operation, we should use the metal based membranes. And now what are the strategies that we can use for this? If we want to enhance, or if you want to enhance the mechanical stability, more inorganic material should be incorporated, more process optimization, it should be generating minimum waste. So, these kind of strategies we should be efficiently operation. Now, in terms of fuel cells or hydrogen generation efficiency, we have been able to reach the efficiency of 60 to 80% in the range for the PM category, but this is again subjected to various operating conditions. So, in order to enhance, or in order to have a widespread application of this technology, we need to further work on the stability of these membranes, so that we can enhance the efficiency. Now, what is durability? I was initially mentioning in a study that we go for different testing of our membranes, like whether it is durable or whether it is losing its property or under various cycles in a long term. So, these are the tested or durability that we test in lab, but in real life that we can have the reduction in durability, we can have reduction in durability due to many aspects, like that thermal stability, if there is a high temperature gradient during the operation, or if there is exposure to some chemical, then our durability goes down in real life. Or you can have again, for increasing of durability, you can, other than the composite deposited onto your membrane as matrix, you can have protective coating, protective or insulatory coating on the membrane surface. Okay. And you can have structural reinforcement, like say in kind of metallic materials or all infaced into the membrane materiality, so that the durability can be improved. Okay. So, safety aspects. We have talked a lot about the flammability of hydrogen. We already told that even 4% of hydrogen mixed with air, that catches fire. So, but that we have talked about that if there is a tiny leakage, so membrane with leakage or membrane with defect, it is not at all allowed for this kind of operation. One problem that we have not talked about is hydrogen embrittlement. Okay. So, when we are storing hydrogen in any membrane based container or any other condition, one thing we must keep in mind, hydrogen is very reactive also. So, if it is very reactive, then what it is doing is that it is creating lot of reaction with the surrounding material, and the properties of the material, they change, the mechanical strength of this material or this reaction product, they change a lot, and that is practically in gist what is embrittlement is. So, with a long or prolonged use, we have to be careful whether the mechanical strength is being lost or not. Thermal stability is that for if there is any very high contraction and expansion of our metallic material, then also some cracks or defect can occur onto your membrane surface. So, that also has to be thermally stable, like thermal expansion should not be very high for this kind of membrane. Pressure variation, also the pressure coefficient variation, it should be minimized, and that is why we have to have some mitigation strategy like periodic testing. We can have some composite materials, or we can have regular monitoring of the temperature and the pressure system. So, cost analysis is mainly the cost analysis or cost comparison of among the different membrane materials are mainly same as like we were talking about yesterday. We can have lower cost with the polymeric membrane, but we have to be careful with other operations. But what I want to have a view is that this cryogenic storage cost around $5 to $10 per kg of hydrogen, but membrane based storage it costs around 3 to 7 per kg of hydrogen. So, that is one that is much that is lower than the cryogenic, but compressed gas storage, that is that it requires that compressed hydrogen cylinder, or that it requires very although it gives you lower cost, but it requires high storage space, it requires many safety regulations, etc. Environmental impact, of course, it gives you lower carbon footprint, it gives you lower amount of waste and material. But one thing we have to be careful is that if our membrane materials are spent, whether they are safe to dispose to the environment or not. So, there are some safety protocols which we will be talking about in our in my last lecture. So, some safety protocols we have to keep in mind whether they are safe for discarding in the environment. And also we have to be careful about whenever we are installing any hydrogen storage system, membrane based system or otherwise, we have to be careful about the whether there is any hydrogen leakage happening or not. Now, let us see some of the industry case studies, whether these membranes has been really applied and proven to be useful. Okay. So, there are two companies, Air Liquide and Linde Group, where they have used hydrogen separation by using a palladium based membrane. Linde Group, they are a German company, they have these deployed polymeric membrane for hydrogen refueling station. They have used this in real life and they have got successful results. In aerospace, I was telling that NASA is implementing cryogenic membrane system for storing of hydrogen. Boeing is also doing the same, and Airbus, they are having these kind of different membrane based technologies for the future hydrogen aircraft. So, these Airbus and Boeing and NASA, they are not applying it in a large scale system, but still it is in testing system, but they have proven or they have given much good results. Anyone is interested to buy this car, Toyota Mirai? What is so important about this car? So, it is going to come in Indian market very soon. This is a hydrogen powered vehicle, which is which will be using a hydrogen fuel storage system in it. So, in this system what they were going to use is that this Toyota company they are going to use is that they are going to have a composite membrane inside the connection between the fuel cell and the hydrogen storage tank, okay, inside their car. So, in this they have a very very high means high reduction in the cost of this car. So, that is what they are claiming. So, this Hyundai is also working on such kind of membrane and they are also we can expect some of this solution from Hyundai also. Other than these, you can have application in maritime industry also. You can have we are seeing its application in heavy duty transport, and industrial manufacturing. Siemens is using ceramic membranes because they are using it for electronics purpose, and chemical and petrochemical industries, Shell and BASF, they are also using hydrogen and they are having membrane based systems for the hydrogen storage and refining. So, these systems I have already talked about the first two. In the Japans, they are also having a palladium alloy membrane which is giving you hydrogen based, they are storing, they are making energy and giving it to the energy grid. Okay. So, if we have a look on the recent developments or what is the future of these membrane technologies. So, apart from the nanostructure membrane and composite membranes, we are also looking into the AI driven membrane, the smart membranes. What are those? That if there is any change in the surrounding condition, then the membrane itself will change its properties. Okay, it will change its properties and will its efficiency or its pore size or its control will be differently tuned. So, that is what AI driven membrane design is being very much popular nowadays. So, a lot of research is going on. Apart from that, most of the materials, most of the considerations are into the material consideration, so that you can reduce the cost and we can reduce the complexity of the systems. Okay. So, these are some of the future trends like hybrid and smart adaptive materials, MOF based technology or membrane based hydrogen transport, which we can expect in different temperature in coming technologies. So, I was briefly mentioning about this smart or nanostructured material. So, one of that I was telling that they adjust their permeability and selectivity based on the environment. So, like for example, these particular MOF they have reduced by using of this AI. One particular paper in here they have shown that this particular MOF they can reduce your energy demand by 7% reduction in energy demand by just using the AI based technology, by reducing its or tuning its permeability through it, which is an interesting concept because you are using the same material and you are practically giving it command to change itself because of there is a change in the environment. There are some purity standard, like same purity standard for this storage system also. So, in the international hydrogen purity standard are like ISO, ASTM standard, and fuel cell vehicle has some industry specific standards, and aerospace and semiconductor industries, they all of them require almost 100% purity. And membrane based technology for hydrogen purification, it is that they have they can have very almost 100% purity of these membranes. So, government has taken up some policies and regulations. They have been giving different grants in United States, Japan, and recently in India also we have the National Green Hydrogen Mission, where they are employing more and more focus onto the large scale hydrogen generation and the hydrogen utilization. So, that is all about the storage using membranes. If you have any question, please feel free to ask. Yes. Thank you.
Hello.
Yes, so if we are not changing any other thing, just by changing temperature you can control the desorption. So practically if you see that it is an endothermic process, if we have an absorption process, so when we are controlling the temperature, so then we can actually switch between cycles by reducing the temperature and increasing the temperature. That is one possibility that you can do. Other than if you are trying to keep the temperature constant but want to still switch between cycles, then you have to use different materials mostly. So temperature is mostly sensitive, very sensitive for hydrogen absorption and desorption cycle, or otherwise pressure. Yes, pressure has a effect. You can switch different low pressure operation and high pressure operation to switch between cycles of absorption and desorption also. But in that case, if you change the material, then obviously you can have an absorption and a desorption, two separate system in a cyclic process. That is also another option that you can have.
Ma'am, here in this palladium based membrane, so different compounds are having hydrogen. So every time, how do you optimize your membrane thickness or the amount of what is the area of membrane you need for specific amount of hydrogen output? So different components it might change. So how do you optimize that? Means like you have shown one compound, so other compound is also having some hydrogen. So if you use this membrane to separate or store, so again these properties change continuously, or these are like some baseline for any?
Basically, which type of this answer depends on which type of mixture we have.
That is what, ma'am. So every time it changes, I'm asking you
No,
for depends on application.
Yes, yes. So it is practically, let us say that I have a mixture of carbon dioxide, carbon monoxide and hydrogen.
Yes.
So carbon dioxide, carbon monoxide and hydrogen, and so palladium will only transport hydrogen selectively. Okay. So that's why, so if we have the composition changed in carbon monoxide and carbon dioxide, it is it is expected that the efficiency or the transport or the flux or the permeability, permeability itself will not change of the membrane, but the total flux we might see a change because it is a operating pressure dependent, because the total driving force will be changed in that case.
And that is what my question is. What is the, because if the material changes, the driving force may change.
Driving force may change, but permeability itself is a specific property of the membrane.
Okay, so so there won't be any reactions with the palladium even though if you use different types of materials also?
There will be a difference, that is what I am telling. Permeability will be remaining same, but effectively the
life cycle may get reduced.
Effective flux can be different. Effective flux or because in metallic membranes are comparatively more regular in structure. So that's why it is easier to maintain the permeability of the metallic membranes. But at the same time your driving force is changing because you are changing your composition of the gas. So in that case, obviously you can change.
With respect to the saturation of membrane, how do you know that it is saturated? Means like, for me, I am using for air dehumidification purpose. So I'm using 1 desiccant, and opposite side I'm sending my dehumidified air. So at one point I know that the membrane is saturated. So it won't, because of this hydrophilic nature or something, it will get saturated and it may not allow the vapor to pass through again, to absorb the vapor and send to the desiccant. So in this particular, how do you know what method you use to check for the saturation?
Basically, the guideline is to check your permeability after every cycle. Okay. So if you are working on the membrane field, then you must be knowing that after each and every cycle there is a washing protocol or there is a regeneration protocol. So after this regeneration and washing protocol, we generally check the permeability of the membrane. It is often not possible to regain the initial permeability. So there is a loss, maybe 10% loss at one cycle, another cycle maybe 5% loss. So if the loss in the permeability is too high, which is not acceptable for your specific condition, then you can say that the life cycle is over. So it can be very much application specific for the case. Okay. So what is application specific is that for your application, what is the amount of contaminant that you can allow in your treated stream. That is actually the main deciding criteria,
Yes.
up to which you are reaching within you are remaining within the limit.
Thank you.
What's the fabrication method generally used to this hydrogen membranes, like to enhance durability?
Yes. So actually, for polymeric membranes, as I was once mentioning that for polymeric membranes, when we are using this solvent non-solvent method, it creates a pore volumes of a larger size, which we do not require or which we want to avoid in this kind of hydrogen separation application. So in that case, we need very thin or very dense material. So one of the technology that we can do is that by evaporation of solvent. Okay, so by casting, after casting, we keep it under vacuum or at a inert temperature. That is the one possible solution. Other possible solution is that like sintering of the membranes, sintering of inorganic materials, which will give you more dense structure. Okay, basically that are used for inorganic materials. Okay, or you can have coating of your membrane onto a surface. Okay, I was showing once in a palladium coating method being used in a rolling machine. Okay, so these are the some of the economics which we have to keep in mind that the pore size should be minimum as possible. It should be thin and it should be also very low porous.
One more question related to that purity. Suppose if I am not able to maintain that 99.9%, so can I use that type of product also for other type of membranes? Like is purity is all depends on basically the poisoning of this carbon monoxide and sulfur only, or any other?
No, actually when we are having this PEM fuel cell or others, then we need very high purity of hydrogen. But hydrogen is not only used in energy application, they are used in as a reactant in many other places also.
For example,
Obviously.
for refineries we use it as one of the ingredients.
Yes, exactly. So in that case, maybe 10%, maybe 90% purity level is acceptable. So that is there. So we can have sequential membrane process to enhance the purity of the level, or other process like that. Okay.
Also, material of construction, how it is different from these cryogenic and compressive basic techniques. Like we use different type of materials. As you mentioned in one of the slides, the cost reduction happens with respect to this membranes utilization compared to the cryogenic cutoff. But in cryogenic, I think most of the time use alloy-based materials. Is it costly, or is it reducing cost in membranes kind of a technique?
In cryogenic, I showed that in cryogenic we use the membrane only at the exit part of the from the tank actually. So membrane, what it is doing is that if we have a membrane which can selectively allow hydrogen, then instead of storing pure hydrogen, we can store a mixture. So that's what I was telling. So you can use pure palladium. Obviously, if you have alloy, it will reduce the cost.
And one more problem with respect to this cryogenic things, the rapid phase transition happens. Inside that, liquid converts to vapor, then vapor converts to liquid. So because of that, temperature, pressure fluctuations are there. Is there any kind of a problem associated with this membrane kind of a technology? I mean, membrane, by using these membranes, there is a pressure. And you shown some of the slides, there was a temperature effect also there, and pressure also, like continuously variation with the pressure. The amount of flux also varies, particularly with respect to some of impurities if it is present.
Yes.
That affects
It does. It affects. Obviously, it affects.
And with prolonged usage, the mechanical strength of the membrane will it gets damaged.
Embrittlement, that is called
So
embrittlement.
the volume of the storage capacity also will decrease, right?
Yes, embrittlement has not only storage capacity, it has a risk factor associated with it.
Like if we suddenly, if we just put the same storage and there is like spoil of the membrane, then it might lead to explosions also. So that we need to consider during.
Yes, obviously. That is one of the, I have shown some safety regulations. This is one aspect of the safety regulations, that how much, at what condition it does embrittle. Okay, at what condition it breaks, it loses mechanical strength up to a certain point. So these are all testing procedure. Okay, I will explain more about these safety regulations in my last lecture. So it's like very, very important, especially for hydrogen energy.
Ma'am, you have discussed about metal organic framework as well as geolite imidazole frameworks for this membrane technology. Why aren't we using this COF, like covalent organic frameworks, often in this? Because they are more rigid. We can also, control the thin and thick layer, and as well as we can, tune the pore size as well. Why aren't we using them like COF? I haven't seen any.
Why am I not using
No,
POF?
no, I didn't see any application of covalent organic frameworks in this membrane. So I was curious, like whether they are used in these particular membranes or not. I don't know.
Can you speak again, or maybe your A is not clear?
Like I am asking, like
No, which term you are using?
covalent organic frameworks.
Polen organic framework.
Covalent.
Polen organic framework. I think they are still in the development stage. They have not been tested very widely in membrane technologies till now. They are still in the material development stage in the because if before using it for membranes, we have to ascertain certain properties, whether they are stable, whether they are mixable with these polymers and all. So I have not yet. I might be I need to expand my search field, but I have not yet encountered any reports onto membranes mixed with POF. I did not see it anything. Probably they need more research onto this kind of into this line. Yes. That's all. Yes.
Perovskites usually they are very unstable materials.
Yes.
They quickly oxidize.
Yes.
So how are they being used for?
Where did I mention? Did I mention in the ceramic?
Ceramic. That's okay.
In the ceramic.
In the metallic.
So I think I have mentioned it with as a material for alloy.
Okay.
As a material for alloy. So they can be like a material for a inside layer.
Okay.
Okay. There should be a protective coating above it, obviously. So perovskite, whether they are unstable, but at the same time they offer a lot of mechanical strength and the thermal stability.
Yes.
So that's why they can be used as a composite material, not as a sole membrane. Obviously, for the reason that you have mentioned, they are not stable, not stable when exposed to the hydrogen. So thank you all for your attention. I now hand over to Professor Vedanpur for the next session. Sorry, it took more time.
Please play video 4 before beginning. This is the hollow fiber production line. We have an injection pump for injecting the polymeric solution. Fill the cylinders for injection. In hollow fiber, we have bore fluid. That bore fluid should be inserted in the spinneret for precoagulation and producing of the hollow fibers, lateral tube. This is the injection pump. we see similar to the nanofiber production. We have two pump, one pump for bore fluid, one pump for polymeric solution. This is polymeric solution, have viscosity. Previous one was water, no viscosity. We can control how many milliliter per minute the bore fluid or polymeric solution can be injected. We can control the pressure of pump. As you see in here, it is better, began the fibers production, give with hand. Usually about 20 meters will be waste. Now this rolling can strengthen the membrane. The speed of this rolling is important. With the increase of the speed, we can reduce the size of the hollow fibers. Okay, go to PowerPoint. We say that we have many parameters should be controlled in the fabrication of membranes with phase inversion. In this slide, we show the effect of solvent. With change of the solvent, the porosity, flux, rejection, all can be changed because with change of polymer, with change of solvent, with change of temperature, the viscosity of the casting solution can be changed and cause to the change in exchange rate. In this slide shows that the slow exchange rate and fast exchange rate how can cause in the different mechanisms. With the phase inversion, we can produce spongy and finger-like membranes only with change of the polymer and solvent. In this slide, our polymer is cellulose acetate, and with change of the solvents, all of these solvents can be dissolve the cellulose acetate. The concentration is similar, 15%, but we see that the DMS or NMP, DMF have the high membrane water contact or porosity. This shows that in these solvents we have the high porosity, but in these solvents we have a low porosity. And we have a solvent solubility parameter I will discuss about in the green solvents in the 4-day. Every solvent have a solubility parameter, and this solubility parameter can cause that one polymer can be dissolved in this solvent. With having of the solubility parameter, we can predict that a solvent can be dissolved, a polymer or not. I will discuss later. You see that with increasing of solubility parameters, the porosity of the resulted membranes increase, and with increase of solubility parameters, we have a rapid precipitation, and with rapid precipitation, we have a high porosity that causes to the high flux. The thickness can be also influenced in the membrane. Generally, we know that the higher thickness can reduce the flux because the mass transfer will be related to the thickness. But the morphology of the membrane also can be influenced with thickness. When we cast the membrane, the casting liquid, with lower thickness, we have obtained a spongy structure. Our solution is. But with increase of the membrane thickness, we see that we can produce the macrovoids. Therefore, the thickness of the casting also can influence in the membrane structure. The coagulation bath temperature can be influenced. The non-solvent composition. In most cases, we used pure water, okay? But we say that when the polymeric solution come to the water, the solvent go to the water, okay? And after 10 minutes in the continuous production of the membranes, our water, our non-solvent is not impure, is not pure. Because the solvent come to the water and we have 1%, 2%, 3% of the solvent after 10 minutes. Therefore, in industrial state, we have not pure water as a non-solvent, and we have 2, 3, 4% of solvent. Therefore, we must investigate the effect of the solvent as an additive in the non-solvent. In this study, with use of the non-solvent as a 2-butanol, pure water, mix of water and isopropanol, and mix of water and butanol. We see when our non-solvent is dobutanol, the morphology is spongy mostly, with a finger-like only on the top layer. But in water, we have a very porous, but in the mixture, we have a low porous. Therefore, the composition of non-solvent and inserting of the solvent to coagulation bath can change the morphology, and the morphology influence on flux and separation. Air humidity during the casting can influence. In this study, this diagram shows the humidity influence on rejection and pure water flux. We see that with increasing of air humidity, the flux increased, but the rejection very low decrease. With increasing of humidity, our process from non-solvent can be changed to the VIPS method, vapor-induced. In vapor-induced method, I say that we have a NIPS, IPS, TIPS, VIPS. In the VIPS, vapor-induced, after casting of the membrane, we put the membrane in a chamber having vapor. When we have a high humidity, like as India, now I think we have a 80% humidity in weather. But in Iran, we usually have 20 humidity. In Istanbul, 30, 40. Okay? Therefore, the fabricated membrane in India will be different from the Iran if we do not control the humidity. Therefore, the humidity, you see that with increasing of humidity, the flux increase and the rejection slowly decrease. And we see that SEM image of these membranes with high humidity, we see this, we have a very big pore size. But in medium humidity, we have a narrow pore size. For discussion about the exchange rate, phase inversion, and what happened during the solvent exit and water entrance and exchange rate, we used phase diagram. In the phase diagram, we have a polymer that dissolves in solvent, okay? And when we prepare a casting solution, for example, 20% polymer in solvent, we have located in this area, this typical casting solution composition. This point will be located in this line. But when we, after casting of the membrane and put it in the non-solvent, that water come to the solution and solvent exists. Therefore, this point began go to the left. And we have a movement of this line, and when reached to this place, that the final membrane, in this place we have not solvent, and we have a polymer and non-solvent, and all porosity of the membranes will be filled with water, and all solvent will be removed. We have some areas in this diagram. We see this is glassy region, this gel region, and this one phase uniform region. Okay? For preparation of membrane, we usually prepare the solution in this area. In this area, we have a stable solution. That means when we have 2%, 3%, 5% of water in the polymeric solution, the polymer solution is stable. With addition of 2%, the polymer solution do not change to the solid. Okay? But with addition of the water, when we reach to this line that is named binodal boundary, the stable polymeric solution start to unstable, but not completely unstable. We say metastable. It is the between unstable and stable. This white area is stable, this gray is metastable, and this area is unstable. When the composition reaches to this area, the liquid will be solid. In this area, we have a solid membrane. In this area, we have a turbid area. As you see in the video, first, when we put the membrane in the water, the color is changed. And the film first turbid, and next become white. Okay? This is a stable, a metastable area. And you see that this area white can be different. In this, when we have this solution, this go to the right, reach to this area. When we have this concentration, this reach to this area. That means the white of this area is different. And this metastable, in most cases, produce the morphology. And with change of the composition of the casting solution, we can change the metastable region area width, and this goes to the membrane final structure. After addition of the most non-solvent, we have reached to the spinodal boundary. That spinodal boundary is the boundary between solid and metastable area. After spinodal boundary, we have a membrane, solid membrane, and we give time that this point reach to this area for production of a membrane. All of these diagrams, these lines, have a thermodynamic and kinetic equations. And you find one book about thermodynamic and kinetic of phase inversion. Some scientists also study in the kinetic and thermodynamic change in the phase inversion and draw this diagram. For drawing of this diagram, usually titration is used. We have a polymeric solution. 1 drop water is added, good mixed, and with the light, the turbidity is measured. When reached to the solution is turbid, but now is liquid, we reach to the binodal area, and when we add the final drop, that after adding and mixing for 1 hour, the obtained solid is not redissolved, we reach to the spinodal line. Therefore, for drawing of this diagram, maybe we need 2 months time. One student in their thesis, is his thesis, 2 months every day should be prepare solution with different concentration, and add drop to drop water. 1 drop add, drop is solid, but 1 hour is tiring to complete dissolving of 1 drop. Again, 1 drop, 1 day for 1 point. 2 days, 3 days for design and drawing of this diagram. 2 months time is needed for completing. With change of the polymer, diagram is changed. With change of solvent, diagram is changed. With change of non-solvent, diagram is changed. Therefore, if we want to for example, investigate the effect of solvent. We select 3 solvents. We must 6 months in lab analyze and test for drawing of the diagrams. But this diagram is very important for prediction of the membrane morphology and why one membrane is spongy structure, why one membrane is finger-like and others that I have not time for more discuss. I go. For example, with change of D match and NMP, D match in the left and very difference in binodal line. This is binodal. With change of the very little in the white, we see that the D match and NMP have very different structure as seen in the previous slide. In this slide, we also can see that with change of the molecular, with change of the polymer concentration, we have a similar, different structure. There are 16 parameters for obtaining the membranes. In this slide, I show that in commercial UF membranes prepared from CSM coach AMI from India, Dow Film Tech, Hydronautics, Toray, where I go? Most used polymers is polysulfone, PVDF, cellulose acetate, acrylonitrile, polyacrylonitrile, and polyamine. Okay? As you see in the commercial UF, mostly polysulfone, polyethyl sulfone, PVDF, some cases PVC, some cases polypropylene. But PVDF and polysulfone is usual because of a high durability and good chemical and mechanical resistance. The second most used phase inversion is TIPS, thermal induced phase inversion. In non-solvent NIPS, we say that the non-solvent goes to the solidification. Okay? In the TIPS, we have a two situation, two category. One category is most used in high temperature, and a solvent can dissolve a polymer. For example, in 150 centigrades, a polymer can be dissolved, a solvent can be dissolved a polymer. But if the temperature reduced to 70, the polymer will be dissolvable, okay? Not soluble. Therefore, in this technique, in high temperature, we prepare a uniform solution, and in high temperature, we cast, and next, let to L02 reduce the temperature. When the temperature reaches to 70, solution will be changed to not soluble, and phase inversion happen, okay? With reduce of the temperature, the solubility is removed, and a soluble solution will be changed to the unsoluble, and we no need to the non-solvent. And this name as a thermally induced phase separation. Therefore, in the low temperature, we have a immiscibility. We can use PVDF polyethyl sulfone for this purpose, but the used solvent is different. In NIPS, we use DMAC, NMP, DMF, DMSO, but in the TIPS method, the solvents are changed. We used dimethyl phthalate, diethyl phthalate, dibutyl phthalate, dioctyl, all of the phthalate groups, and all of these solvents is oil. This most use of, for example, DOP is used as a stabilizer in the PVC for flexibility, increase of PVC. Okay, after preparation of PVC tubes, usually 2%, 3%, added DOP or DPT for increase the flexibility and reduce the brittle of PVC tubes. But in this case, we dissolve PVDF in DOP, DBP, and in room temperature, DOP cannot dissolve PVDF. For dissolving, we need high temperature. After high temperature, we cast the films and allow to decrease the temperature. As you see in this diagram that is named upper critical solution temperature, such as PVDF in DOP, we have an unstable regime and stable, okay? In high temperature, in this area, for example, in 150 centigrade, we have a single phase and stable solution, but with the reducing of the temperature, we come to the unstable area. And in this area, this is a binodal. In this area, the phase inversion happen and the liquid change to the solid. Most of the tips in this method, but we have some solution with reverse behavior. We say reverse tips. Some solutions in low temperature is soluble, with increase of the temperature is non-soluble. Most of polymers have this behavior, but some solvent and some polymers have this behavior. Mostly with change of solvent, this behavior change. Therefore, in reverse tips, in room temperature, the polymer can dissolve in solvent. We cast the film and increase the temperature. When reached to 100, liquid change to the solid. Therefore, in this case, we have a LCST. We see upper CST, critical solution, and lower. Most we have this process, but in some cases we have this behavior. The prepared membranes with the tips have larger porosity and uniform pore size. The NIPS problem is that we have not uniform pore size. We have a wide pore size, one big, one small. But in the tips, we have a narrow pore size, and this reduces the fouling. You see that the polysulfone with NIPS, this morphology, but with the reverse tips, have this morphology. The effect of coagulation bath temperature on tips also important. After the solidification, okay, we have a film that have solid, but the solvent is here, and we must remove the DBT, okay? Therefore, after the membrane fabrication, we put the tips membrane in the coagulation bath for remove of the solvent from the prepared membrane. Membrane is prepared, is solid, but for remove of the solvent from membrane, we put the membrane in coagulation bath. Therefore, in tips, we have also coagulation bath, but this coagulation bath is not for solidification, only for remove of the solvent, okay? Therefore, after tips, we have a coagulation bath, and this show the coagulation bath effect in the membrane structure that in lower concentration of the polymer, lower, the coagulation bath temperature can be effect, but in the higher concentration, usually have not effect. Therefore, coagulation bath also can affect on the efficiency of membrane in tips method. And the final method, VIPS, I say that in the VIPS, we have a vapor chamber, and we have used usually vapor of water for producing of the membranes. I say that with increasing of exchange rate, the pores is low, small. Okay, the next lecture, I say that in the exchange rate, when we have a high exchange rate, the pore size will be small. If we have a low exchange rate, the pore will be big. In the VIPS, we used vapor of water instead of direct water, okay? In NIPS, we put the membrane in water. The concentration of water is very high. But in the VIPS, we put the membrane in contact with vapor, that the concentration of the water is low. Okay, vapor is in the mixed with the air. Therefore, when concentration of the water reduce, the exchange rate reduce. Okay, when we use VIPS, the concentration of the water reduced because water is dispersed in air. We have a vapor, and this caused the slow exchange rate, and slow exchange rate caused to the big pore. Therefore, VIPS is used for fabrication of microfiltration membrane mostly. Okay? Therefore, VIPS used for microfiltration, because instead of liquid water, we used vapor water. The exposure time to the vapor and the vapor density or vapor percent is important. In these membranes, the humidity, relative humidity is 100. The air is saturated from vapor. When we say 100 relative humidity, that means that most of the gas phase is air, nitrogen and oxygen. And humidity, vapor, reaches to the saturation concentration. In this gas phase, in the vapor phase, 1% is vapor, And most phase is nitrogen and oxygen. You see in this one that with increasing of the exposure time, 10 minutes, 6 minutes, 5 minutes, 3 minutes, 0 minutes, the morphology is changed. Therefore, exposure time and humidity is important. In this case, we see for exposure time also, and see that the morphology can be changed with exposure time. Okay, this presentation for